Now let's say we have multiple such processes. Clearly we will need copies of these user-level thread structures, process control blocks, and kernel-level thread structures to represent every single aspect of every one of these processes. So we'll need to start maintaining certain relationships among them. With respect to the user-level threads within the threading library, it keeps track of all of the user-level threads that represent a single process. So there is a relationship between them and the process control block that represents that address space. For each process, we need to keep track of what are the kernel-level threads that execute on behalf of this process, and vice versa. For each kernel-level thread, we have to make sure we know what is the address space within which that thread executes. If the system has multiple CPUs, we need to have a data structure to represent the CPU, and then we need to maintain a relationship between the kernel-level threads and the CPU. So what is the CPU that a kernel-level thread has affinity to, last ran, was scheduled on, and then for a CPU, a pointer to its current thread or a pointer to the threads that typically run there, and similar information. When the kernel itself is multi-threaded, we said we can have multiple kernel-level threads supporting a single user-level process. When the kernel needs to schedule or context switch among kernel-level threads that belong to different processes, it can quickly determine that they point to a different process control block, so they will have different virtual address mappings, and therefore it can easily decide that it needs to completely invalidate the existing address mappings and restore new ones. In the process, it will save the entire process control block structure of the first kernel level thread, and then if it's context switching to the second one, it will restore the entire process control block structure of the second one.